All right, so today we're going to move on from looking at conformations of molecules like butane that were just straight chains. And now we need to talk about cyclic conformations. And specifically, we're going to look at the most common ring size, which is 6. And so these are going to be conformations of cyclohexane. So if we recall our review of Vesper theory and your Gen Chem knowledge of Vesper theory, when we have an sp3 hybridized carbon, the bond angles that are desired for tetrahedral anything, but sp3 carbon, the angle for that is 109.5. So if we have methane like so, I haven't really drawn it to scale here, but the angle in between all 4 of the hydrogens should be 109.5 degrees. But then if we draw cyclohexane and we say, okay, this cyclohexane, we'll do methyl cyclohexane. If we say this cyclohexane is flat, it's all the atoms are in the plane of the board. What would the angle be for those bonds? It's going to be 120. So this is, here I'm talking about a carbon to carbon to carbon bond angle. So if this sort of thing happens where we have a disconnect between what we want to have and what we should have, this creates what we call ring strain. And I think that term is pretty logical, right? If the ring is not a right size, it's not a happy size, the carbons can't move into those 109.5 degree angles that they want. And so that causes some ring strain or angle strain. So that's particularly noticeable for stuff like cyclobutane, which is a square, or cyclopentane. However, for cyclohexane, it can bend out of the plane of the board or in various ways. But it can take on a 3D conformation to sort of alleviate, well, actually in one of the cases we'll see, it pretty much completely reduces angle strain and allows us to have those 109.5 degree bond angles that we want to have. So if you have a stencil, now is the time, because we're going to talk about we're really only going to talk about one of them. The first looks like this. And this is called the cyclohexane chair. All right, and actually, hang on just a second. Let me go into my Can I paste an image in here, please? Yes. Okay, hang on, sorry. All right, so so if you think of somebody sitting on a beach chair or a lounge chair, I think beach chair is maybe more appropriate. We've got the sort of seat of the bench, which is sort of the middle part here. And then we have a headrest. Like this one is actually looking backwards. So here's the headrest of the chair, and then the footrest, right? Footrest is right there. So pardon my bad sketching, but there we go. There is a person laying in the chair. Whatever. Okay. So that's why we call it a chair. And then the other conformation, unsurprisingly, is called what? A boat. Because it's a boat, I guess. And do better than that, I think. There we go. There's our boat structure. And, well, in the chair, the headrest and the footrest are parallel to each other, roughly. In the boat, right, it's a U shape. We're going to focus on the chair structure because this successfully alleviates essentially all, technically there's still a tiny bit of angle strain, but it eliminates pretty much 100% of the angle strain. Okay, so let's build this. Hello. You. So let's build this. Just use the carbons. Don't worry about hydrogens yet, although we'll get those in a second. So don't really think too much about the boat initially. Just build cyclohexane. And remember that your carbon pieces have 109.5 degree bond angles. And so if you try and build a flat hexagon, you're going to notice that the bonds are going to get bent a little bit. 1, 2, 3, 4, 5, 6. So if I try to put together a flat hexagon, the plastic pieces are being bent very slightly. If you do this, you'll probably notice this. Of course, don't break your modeling kit. But if you, I don't know, you kind of have to finagle the model a little bit. But you should be able to get it to go kind of into a chair conformation. Just wanted to behave nicely. But I don't know, you can kind of see it here. Bend a little bit more. Ooh, there we go. Better. But if you look at the 4 carbons that make up the seat, you'll see there's a headrest on your left and a footrest on your right. Okay. When you set it down on the table, it should not sit flat. All right. Let's while we have the chance, let's practice drawing the chair structure. Of course, if you have a stencil, that makes it easy, but you need to be able to do these freehand. I did it pretty fast there. So let's look at each of the parts that we draw. So first, we want to draw a pair of offset and diagonal parallel lines. So that's going to look like that. Okay, two lines of basically the same length that are offset. They should be diagonal. They can go diagonal the other way, and that'll get you the other shape of the chair, or the mirrored chair. So that's going to be part of the seat of our chair, all right? Then we're going to connect both left ends and both right ends of the diagonal lines with a V shape. And so, right, it wouldn't make sense to go up and down to make a V on that side, because you'd run over bonds and stuff. So you make a V shape like that, and then a V shape on the other side, like so. And to check and make sure you've done it correctly, you should have 3 pairs of parallel lines. Okay, those 2 lines are parallel. Those are the first ones you drew, so they should be parallel. Those white lines should be parallel. And then the 2 yellow lines, I'll have them mostly parallel. Good enough. So 3 pairs of parallel lines. We can draw the diagonal lines the other direction. And then our chair structure will look like that. And these are mirror images of each other. So this you're just going to have to do over and over and over again until it becomes second nature. So that is the carbon skeleton, right? So that's a valid skeletal structure for cyclohexane. You can count the carbons, 1, 2, 3, 4, 5, 6. But cyclohexane is C6H12. Each carbon has 2 hydrogens. And so we should also be able to show the hydrogens in the chair structure. So you could just randomly put 2 hydrogens on each carbon, and that would give you a correct structure, correct connectivity at least. But we're talking about 3D, things in 3D. And so if our cyclohexane chair is in 3 dimensions, we need to show the hydrogens sort of in a good spatial arrangement. Okay, and so there's 2 different kinds of hydrogens on a cyclohexane chair structure. So for this, I'm going to draw 3 chairs, all fairly large. And I'm going to try and make them look better than that. That's happier. Okay, so that's what I'll copy 3 times. So actually, this is going to be first structure plus the second structure equals the third structure. Sorry, again. All right, so the first kind are called axial. All right. So the way that you remember the difference between axial and the other one is by thinking of a globe, right? The if you think of the cyclohexane ring as a globe, the axis of the globe goes vertically, right? At least the way we typically look at a globe. So the axial hydrogens are going to go on vertical lines. And so they look like this. So there's three axial hydrogens that are pointing downwards from the ring. That's this one, and this one. And there's three axial hydrogens pointing up. This one, and this one. And notice those are on alternating carbon atoms. So there's a hydrogen up, hydrogen down, hydrogen up, down, up, down. So that's half the hydrogens. So the axis of a globe, right, goes through the poles. What goes around the Earth?
The equator.
The equator. So the other ones are called equatorial. Now, when you draw the axial hydrogens, your lines are always vertical, regardless of whether they go up or down. Lines are always vertical. Equatorial is a little bit more difficult. Sorry, this is supposed to be in yellow. Equatorial, they're not vertical, and they're not horizontal. They're all going to be at an angle. And this is one of those ones where there's not a super easy way to remember these. But for the carbons on sort of the outer corners, they're sort of pinched in on the outside like that. And then for the carbons in the middle, they look like that. Okay, so if you can imagine this being your, well, maybe you don't really have to imagine it, being your cyclohexane ring, all the equatorial hydrogens are going to be on the outside, on the equator of the globe, rather than going straight up and down. So if we put all of that together, that'll give us the complete structure for cyclohexane with both hydrogens on each carbon. There it is with no color. I don't know. At least for me, I feel like I can see the stereochemistry a little better without color than with color, but maybe not. One thing to point out is I haven't drawn wedges and dashes here. And wedges and dashes are not typically drawn on cyclohexane chair structures. It's kind of implied that you know how to read it. That may not necessarily be true at the beginning. And so you should definitely think about what hydrogens should be or would be on wedges and dashes. Short answer is the axial hydrogens are in the plane of the board because they're all straight up and down. And so the axial ones would not get a wedge or a dash. I won't draw them in here, but additionally, the outer equatorial hydrogens are pretty much in the plane of the board as well. However, this hydrogen on this carbon, right, this carbon is the side of the chair that's closest to us. And so this hydrogen here is coming towards us. So that one, I suppose, could be on a wedge if you really wanted. And on the other side, the corresponding hydrogen on that side is on the far end of the seat of the chair. And so if you really wanted, that could be on a hash. But again, we don't typically draw those in cyclohexane chair structures. Not too short. Okay. So rather than add every single hydrogen atom to my model, I'm just going to use the short bonds to indicate the hydrogens. And by the way, depending on the size of your container for your molecular modeling kit, you may want to just build this cyclohexane chair and leave it like that because we're going to use it a lot. But you may not have the luxury of being able to fit the whole thing in and save it. But you can build one and bring it on the exam if you like.
We can have it already made exam, but
Yes, if you want to have this pre-built, you can have anything pre-built that you like. But you're welcome to bring pre-built things for the exam. Yes.
do we get a note card for the exam?
No note card. Just your molecular modeling kit. All right. So sometimes it can be a little tricky to get everything into the ideal axial and equatorial positions. But once you do, you should see that if you hold your model like so, you should have 3 hydrogens pointing straight up. It should be on alternating carbons, so it should make a triangle of hydrogens going up on the top. Same thing on the bottom. You should have a triangle of hydrogens pointing down on the bottom. And then you should have 6 hydrogens where if you rotate it, they all kind of go around the outside. I feel like Gale's modeling sets might be more, if you have a really sturdy set, it tends to hold its shape a little bit better. And so if you set your model down on the table now, it should be resting on 3 of the axial hydrogens. If it's not, you need to bend things a little bit more. Okay, and those 3 hydrogens that it's sitting on, 1, 2, and 3 axial hydrogens going downwards. So clearly, cyclohexane is one molecule, but generally speaking, we're going to have substituents on a cyclohexane. So let's say that we have, and now I'm going to draw it like a regular structure, and we're going to put one substituent. I'm going to put it on a wedge, and doesn't really matter, but we'll make it a bromine. And so for a structure like this, we have two possible conformations that it can adopt. It's going to pick one of the two, but there's 2 possible ones. So let's say that we're going to view our chair, from the top. So there's our eyeball looking down from the top. Okay, and additionally, right, we're looking at the molecule from the top in this view, I suppose. So top view of the molecule, the bromine is coming toward us. So is the bromine going to point up or down in our chair structure? Up. Yeah, if we're viewing it from the top, the bromine is coming toward us, and so yes.
So on the chair, there's a like fold inward, that would be like the points on a normal cyclohexane.
The parts that fold inward.
So our triangles that go inside of the chair. Like I'm trying to
match the two up. Yeah, let's do that with I'll do that here. Okay. Don't erase. Let's do it this way. Let's number the carbons. Okay, so there's a regular hexagon, and there's our chair structure. And so we could say that 1, 2, 3, 4, 5, 6. Something like that, maybe. But of course, this has rotational symmetry. It's harder to see in the chair structure because the chair structure is 3D. And so we could also say, we could start carbon number 1 down here and say 1, 2, 3, 4, 5, 6. Those are both okay.
Starting at where you should get number 5.
Yes, you can do that too.
So
You can start wherever you like. And in fact, it might even be a good idea to practice starting in different places. That way, when I give you a chair structure, you can sort of better see the ability to kind of rotate the structure around. Okay.
The branch, if I want to start like the carbon, like lowest sub
Like for well, so we can put the bromine on any of the carbons. But I'll put it on carbon one. I'm just so I started numbering here at the top at number 1. But you could just as easily say, okay, well, the bromine is here. So this will be carbon 1, 2, 3, 4, 5, 6. That's also okay. Okay, so if we're going to say that the bromine is on that carbon and that carbon is number 1, these are actually going to be our 2 different chair conformations of bromocyclohexane, where the bromine is going up. Okay, I should note here that the bromine is coming toward us. Oop. Oh well. Okay, so if in chair A, if the bromine is going up and it's on carbon 1 in structure A, is it axial or equatorial? Axial. So there are 2 positions for carbon 1, and the bromine is going up, and so the other substituent that's going down is a hydrogen. What about structure B? Is the bromine going to be axial or equatorial? So our 2 possibilities for carbon 1 are there and there. So the one that's going up, in this case, is that one. And so axial here, and equatorial here. So these two structures are not equivalent because axial and equatorial positions are different, but they're both represented correctly by this structure, which does not have any conformational information in it. So let's do another example. We'll do two substituents. Fun. No, we'll keep it at one. Mono-substituted. So if we have cyclohexanol, there's, well, a bunch of different ways that we can draw a chair structure. The most important thing, though, is that the OH group is going down. Okay, so we can put it on any of the 6 carbons in the chair as long as it's going down. All right, so if we wanted to put it on this carbon, we could make this carbon number 1, right? Where is the OH going to go? Equatorial. Yep, so it's going to go to the left and down, kind of like this. Sorry, OH.
Is it going down because it has the hash and it's going into the thing?
Yes. Yep, and so reviewing from the top. In fact, we always view from the top like this. So if you've got something on a wedge, that's not a wedge. That's a hash. Hello. So hash equals going into the plane of the board, and that means it's going down in the chair structure. So we could do it like this. We could have the chair going the opposite direction. Right, that's sort of the mirror image of the chair. Let's pick, oh, I don't know, this carbon. Okay, if the OH is on that carbon, is it axial or equatorial?
Axial.
Axial. And it's going to go straight, no, it's going to go straight down. In this case, there's not really enough space to draw it. So what we'll do is show it going way down like that. And that's acceptable as well. Okay. So I told you that these two conformations with the bromine one and in the same way the alcohol, those two conformations are not the same. However, they can flip-flop in between, right? So a molecule can go back and forth. Well, a mono-substituted cyclohexane like this can go back and forth. So let's do this. So we have a methyl group that's axial and up. Okay, axial and up don't mean the same thing, right? Because we could have an axial methyl group here, and that's down, but we don't have that, so don't draw that. Okay, axial and up are not mutually, I don't remember the words. Yes, they're not synonymous. So don't get those confused. Okay, so a ring flip is kind of a chemical, we draw it like a chemical reaction. And one thing, this is a common misconception and something that's easy to mess up, is a ring flip is not just taking molecule and flipping it over like a pancake. Okay, that's still the same molecule. What we're actually doing is, and this is hard to do with the model, is rotate each of the bonds to make the ones that were down go up and the ones that were up go down. Yeah, I messed it up because it's almost impossible to do with your hands. I think I did it. Have to put some substituents on it to make sense. But we can do it with the model. It's actually easier to see in the drawing. So when we do a ring flip, we have to draw the mirror image of the chair shape. Okay, so in this chair, I drew my starting diagonal lines like this. Okay, those are these lines. In the flipped chair, they have to go the other way. All right, so the headrest and the footrest are going to be on opposite sides. Okay, chair facing the other way. We can also make it look more chair-like if you more like that. So the methyl group is on that rightmost carbon. Okay, that carbon is now here. All right, the chair has been sort of not origami, it flipped, but all the carbons that were pointing up, so like the methyl group carbon, these two carbons, are now sort of on the bottom part of the molecule. Okay. However, the methyl group that's on that carbon is still pointing up. And so if we ignore the fact that we just did the ring flip and say, okay, we want to put a methyl group on that yellow carbon going up, it has to be equatorial. Still up, but now it's equatorial. It's kind of like a twist of all of the bonds. I always find this kind of hard to wrap my head around, the movement of the ring. It's sort of a squish movement that occurs. And one way you can check yourself to make sure you have a different structure is take your original structure and try and flip it. So I shouldn't say flip, I should say pancake probably. Nope, come on, there we go. So if I try to do that, is that the same structure that we got there? No, most certainly not. The main difference, and the one that's probably easiest to see, is the axial versus equatorial, right? We've gone from a vertical line in the starting material to a diagonal line in the product. And so this does not agree with what's occurred. So during a ring flip, all axial and equatorial positions switch. And the up versus down stereochemistry remains unchanged. Additionally, something that should probably be noted, the order of carbons and substituents in the ring is also unchanged. So if we had multiple substituents, so if we had two methyl groups that were on carbons next to each other in the starting material, in the product, well, we're just twisting bonds, we're not breaking bonds. And so that would also be next, those two methyl groups would also be next to each other in the product. I think I'm going to show an example of that. Yes, I will, when we talk about di-substituted rings. But before that, so I've said that this is a chemical reaction, and the way I've drawn it, it's an equilibrium reaction, and it is. So to explain which of these two isomers is more favored or more stable, we need to look at what are called 1,3 diaxial interactions. So what I'm going to do for this is take our starting molecule here, and I'm going to add in all the other axial hydrogens. Again, I sort of ran out of space inside the ring, and so I just took these axial hydrogens that were in the middle and drew them further up and further down. That's legal and allowed. Okay, so we're talking about interactions between axial substituents in this case. The reason that we call them 1,3 is because if we call our carbon of interest number 1, and we go clockwise, say around the ring, the next upward axial hydrogen, so the next hydrogen that's on the same carbon, not the same carbon, the same side of the ring, so we're talking about the top side of the ring here. The one that's on the same side, top of the ring, is number 3. And if we go counterclockwise, 1, 2, 3, it's also on the third carbon going the other direction. It's not super important that you know how to number it. We won't really be doing that, but that's where the 1,3 part comes from. So what diaxial interactions are is the closeness in space of those 3 things that are all on the same side of the ring. And when I'm talking about side, I mean the top hamburger bun and the bottom hamburger bun. The same goes for the hydrogens down here. Those are all sort of next to each other. And so the diaxial interactions are contrasted with the fact that there's these equatorial hydrogens or equatorial substituents hanging out. I'm going to draw them really small because they're not super important in this case. But there's these equatorial hydrogens. Although many of them, especially these ones on the end, we draw them like they're really close together. They're not, right? So the equatorial hydrogens here are all way on the outside of the ring. And so they're pretty much as far away from each other as it's possible for those 6 hydrogens to be. However, the 3 hydrogen, well, they're not 3 hydrogens, the methyl group and the 2 hydrogens, I like my methyl group. On the top is somewhat in proximity, or sort of close, to the other 2 hydrogens that are on the top. It's easy to see with the dots. Okay, so the axial positions are closer together to each other than the equatorial position. All right. And so just based on, well, the fact that this methyl group, right, it's not just a carbon atom, it's got 3 hydrogens sticking up there. So it's kind of big, relatively speaking. Those are going to start to run into these other 2 axial hydrogens. And so because of that, right, and so that the other option here is for the CH3 to be equatorial. And because when it's in the equatorial position, it's got all that space on the outside. See? Now the methyl group is sticking up way off the side of the molecule, and it doesn't have as much stuff to run into. And so if given the chance, it would prefer to take on the equatorial conformation. And so in the actual molecule, it's about 95% equatorial, 5% axial, roughly.
And that might only be true though if you've got the one methyl group. If you had more, it might prefer an axial position. Is that correct? Just depending.
Correct. So if you've got, well, this is the next example. So yes. So if we have, come on. So let's say that we have TBU, that's tert butyl. Okay, so tert butyl, well, R attached to a tert butyl group is a carbon with 3 methyl groups attached to it. So that's fairly large group, bulky, we call it. So if I were to ask you to draw the most stable chair conformation of this molecule, well, we have to draw one of the structures first. And so when we convert this to a chair structure, the tert butyl group is always up, and the methyl group is always down. So if we pick the first carbon, let's say it's this one. It's typically the one on the upper right is typically the one that we pick as the first carbon, but that's not a rule by any means. So if that's going up, tert butyl group is going up. So that's in an axial position. So where does the methyl group go?
Like the opposite corner going in.
So it's not going to go on the opposite corner. It's got to go on an adjacent carbon. So this tert butyl group is right next to the methyl group. It's on the carbon that's right next to that carbon. And so it could be, if we're continuing that trend where we look at things from the top, it's clockwise one carbon. And so clockwise one carbon around this ring is that bottom right carbon. The methyl group is going down. And so in order to go down at that position, it has to go here. And that's also axial. Okay, so generally speaking, axial is not preferred. We would like things to be equatorial. So if we draw the mirrored chair, which is the easiest way to do this, and we say that that rightmost carbon is still the yellow carbon, and then the blue one is counterclockwise from it. Okay, tert butyl still has to be going up. We can't change that. Now it's equatorial. The methyl group that's on the blue carbon, still down. And still equatorial.
Still equatorial? We did it change.
Sorry. Yes, still well, still down, but now it's equatorial because we did a ring flip, so we have to change the axial versus equatorial. Thank you.
The ring flips are we go from axial to equatorial.
Always and forever. Yep. Also, maybe this goes without saying, but if you've got two substituents that are both axial and you do a ring flip, well, they're both going to be equatorial. Okay, that actually didn't answer Lynette's question, but the next example is going to answer that question.
Which carbon you start on?
Nope, it does not.
Would it be?
Would you, if you want to pick one that's always that will never confuse you, use this carbon.
On a test, would it be beneficial for us to number for you which one you're starting with at a convolution?
That would probably help you more than me. Because it doesn't matter. But if you number everything every time, you'll never, I don't want to say you'll never get it wrong, but you'll be much less likely to get it wrong. Okay, so when deciding between these two conformations, which one is more stable? Well, both of these are in the equatorial position on the right-hand side, the structure on the right. And so that one's going to be more stable because we don't have those axial things bumping into each other quite as much. However, if we have a very slightly different molecule. The only thing I'm changing here is the methyl is now also on a wedge. Okay. You should be able to draw this one. So tert-butyl going up on the yellow carbon. That's axial. Methyl group clockwise one position and is also going up now. Ah, so it's equatorial. So notice that there isn't necessarily a correlation between the wedge and the dash and axial versus equatorial, because you look at this and like, oh, those are both on the same, right? They're both on a wedge, but careful, that doesn't mean that they're both axial or both equatorial. In fact, if they're on the same type of wedge or hash and they're right next to each other, they're going to be opposites. But don't try to use that as a mnemonic for remembering where to put things. You want to look at the actual cyclohexane chair as you're building it. Okay, if we do a ring flip, well, before I even draw it, if we do a ring flip, the tert-butyl group is now going to be on an equatorial position, and the methyl group is going to be on an axial position. So let's make sure that's correct. Okay, tert-butyl group always going up. Methyl group always going, methyl group is always going up. And so it's going up from that carbon, so I'll draw it way up at the top.
It's like up, but the methyl group's up, but it's still on the inside of the chair.
It's on the side of the chair closest to you. So let me. Is that a little better? Okay. So tert-butyl has gone from, well, they're on sort of different parts of the molecule, but tert-butyl has gone from axial to equatorial. Methyl has gone from equatorial to axial. Tert-butyl is up and up. Methyl is up and up. Okay, so we've done it correctly. Now the question is, which structure is more favorable? Any guesses?
B.
B. Why B?
Is the tert-butyl is larger?
Because the tert-butyl is larger. So axial interactions, as I said, are bad. And so in this structure, where they're both axial, well, those are both unfavorable interactions. And so if we can make them both equatorial, that's great. But here, right, there's competition. So the tert-butyl group here is axial, and so it's interacting badly or deleteriously with the axial hydrogens, but the methyl group is happy out here in its equatorial position away from everybody else. Versus B, where the methyl group is in the axial position and the methyl group is running into those other axial hydrogens. And the tert-butyl group is out on the side, happy. But because the tert-butyl group is so much larger, right? So there's your methyl group. And there's your tert-butyl group. Clearly a big size difference. The tert-butyl group is going to have a lot more issues running into those axial interactions than the methyl group will. So it's more energetically favorable for the big tert-butyl group to be in the equatorial position. Okay, questions on that?
Could you also put the mental group on the, to the left of the character?
Yes, yes, good. So we could have tert-butyl group going up, methyl group goes there. However, if we look at the original structure, the methyl group is one clockwise from the tert-butyl group. And so if we wanted to do that, we would have to, I don't think I can even do it here. Flip it around. No, methyl group's still counterclockwise. Don't have a mirror function, do I? So I can draw a mirror image. So here, the methyl is clockwise from the tert-butyl. And here it's counterclockwise from tert-butyl. This is actually going to be important for next time. So we'll bring this example to next class as well. But these mirror images are not the same. Okay, so to answer your question, the answer is no, you can't go the other direction. You've got to make sure that you continue going clockwise if the original drawing was clockwise. And so if you started with the methyl group, you drew the methyl group first. The tert-butyl group is clockwise from it, and so it's got to go clockwise on the chair structure. Okay, so next time we'll talk about how to differentiate those two molecules and how to name them separately, left and right hands, chirality, things like that.